Okay. All right. So we'll be learning about all these different things in chapter 1. So mass, we'll be learning about different units of measurement, temperature, and really what is science, what is chemistry. We'll be learning about that first. Now, science is the process of seeking understanding of underlying principles in nature. So it is a very concrete science, and it's based on technology and factual evidence more than philosophical theories. But the philosophical theories are what jumpstarts science. That's a very important thing. So we would only know gravity existed if we had Isaac Newton drop an apple off of his terrace, right? Well, we would figure it out eventually anyway. But he theoretically thought of the concept of, oh, why when I throw something up, it comes back down? That's revolutionary. It took us hundreds of years to even think about that. We just assumed, oh yeah, it's just the Earth, it works this way. But it took it took scientists to ask these questions of why it works, or why this is the case, or how it works. So these people are groundbreaking in science. And really, here's a fun fact. Well, not really fun fact, but conceptually speaking, one of my advisors told me one time that what having a PhD or a doctorate is, it's having the license to ask these questions. So I really took that to heart. And it's really having the knowledge and the skill base that you learn from years of education to be able to ask the right questions. And asking the right questions is very important. It leads to theories, which leads to laws that are in nature. So that's really cool. All right, so chemistry, what it is the study of matter and how it changes. So we're going to be learning about everything from your desk and what makes up everything, really. So that's what matter is. Now, air is matter. So you don't see air, but, I mean, our eyes are just tools that our brain uses to understand the world around us. That's a weird way to think about your eyes. But it just takes in light. All your eyes do are very sensitive instruments that take in photons from the environment. And from those photons and our brain recognizing and interpreting those photons, we get shapes, we get different materials, we get light, or we get colors, right? But in reality, all of these molecules and all of this matter is all clumped together, and it's moving around in certain ways, and there's not really any shapes. That's a weird thing to think about, that shapes are just the construct of our interpretation of reality. Mind blown, right? But we don't have to think about that now. But yeah, we're going to be learning about matter. So air, for example, you have the composition of air is 78% nitrogen. So it's mostly nitrogen, but contrary to let's say those of you who didn't take chemistry, a common belief, you might think it's mostly oxygen because we breathe it. But it's actually only 21% oxygen. And carbon dioxide, what we breathe out, is very little. It's actually 0.04% around. So argon gas is more prevalent. And you could be like, oh, what the hell is argon? Well, argon is a noble gas. And we'll learn about that when we learn about the periodic table. And it doesn't really react with anything. And it's just kind of there. And then you have other gases as well. Ozone, right? All right. Oh, the GIFs worked. Hey, there we go. So here's some funny GIFs. You should wait. So which screen do you see? You should be able to see it is a question. Yeah. So do you see the screen that it's full screen, or do you see the little next slide on the right?
I see both.
Yeah, we see
I see both.
Okay.
Yeah.
So you see a double of this.
The definitions are a little smaller and then the GIFs are big.
Wait. So you see one slide and is the gray background with the technology, science, and chemistry on the right?
Yeah.
Okay.
Yeah,
good.
and then the GIFs on the left.
Perfect. Because on I have 3 screens. So on one screen I have all your Zoom stuff. The middle screen I have what you see. And on the right screen, it's actually the full screen of the presentation. So I'll figure that out next week. But anyway, we're here and it's good. So you can see enough. So anyway, I don't like this top GIF. I should take it off because that's not in good taste. This is assault. Get it? NaCl. Yeah, in today's world, I don't think that's a good idea to put this up, but whatever. Okay. And there's some funny science things like explosions. We're learning about a lot of how explosions are, and really oxidation reduction is the cause of explosions or anything explosive. And this is a reaction of sugar with some kind of acid, and it explodes. So that's pretty cool. Okay, so technology. What is technology? So if you know SpongeBob, remember where Patrick's like, "We're not barbarians. We have technology," and he starts smashing the computer against the table. Yeah. So we have technology to help us solve these problems and to help us make sense of the different observations we see around us and to measure them. So technology, you may think computers and stuff like that, but technology is something as simple as a meter stick. That's a piece of technology because it helps us make measurements and understanding of matter around us by measuring it in certain ways. And from those measurements, we can deduce outcomes, or we can deduce theory, hypothesis, and theory, which we'll talk about soon. The science is we know what science is, we know what chemistry is. Great. So green chemistry is a very big emerging subfield of chemistry where we want to eliminate fossil fuel emission, global warming, and all these bad things that are hurting our environment. And lately, environmental cleanup has been very good compared to like the mid-2000s, where we didn't really give a crap about, you see how these graphs are going up? This black line here is the total tons of carbon. And you see from, let's say 2000, like around 1980 to 2000, 2010 even, it's skyrocketing up. And then now recently in the last 10 years or so, the US and other countries have made great strides in cleaning up the environment. And I hope it's going to keep going in that direction. So kudos to us. But a lot of damage already has been done. You know, the Amazon was on fire. Australia was on fire earlier this year and last year too. But that was more of, I think Amazon, someone actually did that. So that's terrible. But a lot of like forest fires are natural processes. So a lot of the times forest fires are good. And that's how the soil and the earth kind of reinitializes itself. It's a kind of primary kind of like rebooting of the earth, and it kind of like there's a lot more nutrients in the soil, and the forests and everything grow stronger than they did the first time. So that's a natural process. But when humans get involved, it makes it less natural. Now, the ozone layer, that's very important. So the ozone layer has depleted. This is 1979. It was about 100%. Then lately, we've been killing the ozone layer. So from the 80s, really, and then it kind of flatlined since. But what the ozone does, so the ozone is actually, you know how oxygen we breathe is O2. So it's actually two oxygen atoms that are stuck together in a molecule. Ozone is O3. Now, ozone has properties that block radiation, harmful cancer-causing radiation, from entering Earth's atmosphere. It's kind of like a shield that we have from blocking these solar rays and solar radiation. Now, once we introduce fossil fuels into the air and different kinds of harmful chemicals, what it does is it quenches this ozone. It could either bind to it, or it could disrupt the ozone molecules by different ways. I'm not actually sure, but I'm actually sure what specific molecular processes, but they disrupt and bind to and kind of quench the behavior of the oxygen O3, and they kind of fall down from the atmosphere, and they're no longer able to block radiation from coming to the Earth. Therefore, we have more solar rays coming in, which can actually, over time, lead to higher cancer rates in humans and other dysfunctions in other organisms. So the ozone is very important. Now, I think one semester, one of my students was like, "Can we just make ozone and put it back?" You could, but look at the units, square kilometers. You need square kilometers of filled with ozone and able to put that up there. And not just 1, 50, 60, 70. So to produce that amount of ozone is impossible. And there is molecular processes and reactions to produce ozone, but it's very time consuming and not really cost effective. Okay, so science, we're not really going to talk about this, but science has 5 characteristics. Really, the only thing that's important is the most important thing is it's testable and it's reproducible. So you can't have something that is scientifically proven unless it's scientifically proven by more than one person. If I measure, if I'm like you've seen that in the lab, it was really basic with the meter stick. But if I measure something and it's 8 inches long, right? Then if 5 other people measure it and they get 2 inches, then what's right? It's not really reproducible. You have to have measurements that are reproducible, and scientific theories or really the data and the results have to be reproducible. And once we do get these reproducible results, then we can bring them make theories out of them, and we can explain them. But before the explanation, we need a hypothesis. So the hypothesis, which maybe if you took biology before, or really any science class, is kind of like an educated guess. It's a little bit more than an educated guess. What it is a testable idea of a testable explanation of what happens in nature, of an observation. So let's use gravity as this example when we go through the scientific theory, because gravity is the easiest one to understand. We observe it every day. Now, Newton was like, all right, he had this just brain blast idea that if you throw an object in the air, or if you just have every object on the planet Earth is kind of tied down to the Earth somehow, why do we need to expend energy to stand up in the morning? He's like, all right, we must be having some kind of attraction to the Earth somehow, to the ground. Now, that's a great question. For someone that is not knowledgeable in this, back then, when no one had any idea, you can think of 100 reasons why this happens. You can say, all right, maybe the Earth is a huge magnet, and the iron that's in our body is dragging us down to the Earth and using magnetic forces. That's totally possible, but you can test that. You can have an object that's not iron, and it will still drop to the floor. So, okay, that's disproven. You can say that there's a magical being in the center of the Earth that's with invisible hands that is pulling every object down to the Earth. You can make crazy hypotheses like that, but you can test that one as well. You can put an object on the moon, and the same thing will happen. It will drop down to the moon's surface. Slower, but it will. So, okay, there's no magical hand that's doing that. It doesn't make any sense. But once you rule out all of these things, you come to the conclusion of gravity, which is, all right, there's this force created by a massive object that pulls less massive objects towards the center of it. And this is called gravity. And he figured this out. And he made the first hypothesis. Then these hypotheses are tested. And once they're tested, they become theories. So they become theories. So a theory is a set of hypotheses that has the same explanation for a natural phenomena. So Newton and a lot of his friends, a lot of other scientists had theories or had hypotheses that they tested, and they came to the same observations and conclusions that Newton did, where, all right, there's got to be some kind of force. It's not magnetic. It's not electrical. It's not a chemical force. There's got to be something else. And they all came up with gravity. It's got to be this gravity caused by the massive object. And based on other calculations, they confirmed this. And then once they confirm it, it becomes a scientific law. So it summarizes the large amount of scientific data available, and that provides a real description and truthfulness of a phenomena like gravity or conservation of mass. So that's pretty cool. And many of these laws, all of them are supported mathematically. So they could do calculations and they could come to the same conclusion that the scientists did experimentally. So that's very important as well. Okay, so the next thing is scientific models. I'm not going to go crazy about that. I know I've been talking for a long time. It's only on slide 15, but I will speed it up a little. Also, if you have questions, don't hesitate to ask. You can ask in the middle of it. Again, this is going to be on YouTube, so I mean, you could ask a question, but if you could just, I don't know. I feel bad saying don't ask questions. Ask questions. Ask whatever you want. But I'm going to try not to repeat myself for like 3 or 4 times because you can see it again later. So, but definitely ask questions. I want you guys to interact and ask questions. Okay, so a scientific model. We are going to be using models because, for lecture and lab, because these molecules and atoms are really, really tiny. They are so small. And we'll talk about exactly how small they are when we talk about the mole. So small you can't even fathom. I can't even understand how small they are. I'm going to make I'm going to make similarities and comparisons to give you an idea. Like, you know those videos that show like size comparisons of like different planets? Those are crazy. Those are mind-blowing to me. Like the Earth is only, what is it, like a million Earths could fit in the sun or something crazy like that. And our sun is like a medium sun. There's suns that are like 100 times, 1,000 times bigger than our sun. That's insane to me. But the atom is the same way, but on the small level. And we need tangible ways of testing things with atoms and molecules interacting. So we use models. And a model could be something as simple as showing the different arrows coming from atoms, showing how they move. So instead of, you can't really see the atoms with our naked eye. And also for models, we scale up everything. So instead of using a reaction of, oh, one molecule reacts with one molecule, we use an entire beaker or entire container of liquid that we can see, accurately measure, and accurately add to another container of liquid. So we use these models. All right, molecules. So this is an important time to, I'm going to add something here. So for molecules, another important thing is compound and atom. Now, these are 3 terms that are very frequently thrown around in chemistry, but not many people know the difference between a molecule and a compound. And for taking this course, it is very important to know the difference. Now, we'll start with the biggest umbrella term. You have a molecule. Also, element is another one that we should know the difference of. We should know what it is. Okay, so a molecule is a group of 2 or more atoms held together by chemical bonds. All right, so an example is NaCl or O2. NaCl is an Na, which is sodium, with a chloride, with chlorine, bound together chemically. O2 is the air that we breathe. It is oxygen number 1 atom bound to oxygen number 2 atom, bound together covalently. We'll learn about that later. And that they're both molecules because they are 2 or more atoms held together by bonds. Okay, now a compound is a little bit different. A compound is 2 or more elements held together by chemical bonds. Meaning, out of NaCl and O2, which one is a compound? NaCl or O2?
NaCl.
Good. Good. NaCl is a compound and a molecule. So the molecule is an umbrella term for compounds. A compound has 2 or more elements that are held together. O2, for example, is just a molecule. Even though they're held together chemically, they are 2 of the same elements that are held together. You could have O3. O3 is ozone. That's still one element, right? It's still just all oxygen, but there's multiple atoms of that oxygen that are held together chemically, making it a molecule and not a compound. All right, so now that we talked about the word element, let's define it. So an element is on the period. I'll just write on the periodic table. That's the simplest explanation of an element. Now the elements are listed on the periodic table. There are no atoms on the periodic table because that doesn't make sense, and I hear that a lot. The elements are on the periodic table: carbon, nitrogen, oxygen, fluorine, boron, whatever. Those are the elements. The atom is the smallest particle of each element. So if I take aluminum foil, for example, it has the element aluminum. It has many, many atoms of the element aluminum. Doesn't have any compounds or molecules. It's an elemental form of aluminum, and it's composed of millions and billions and trillions of atoms. So that's that. Yeah. Okay. So does that make sense? Is there any questions? That's important to understand the difference between these four terms. Yeah, we're good. All right. Good. So good. That's awesome. So next thing is molecular models. I mean, you can have two-dimensional, three-dimensional, different representations of these molecules, compounds, and even atoms and elements. But really, a representation of an atom or an element is just a blob, just a circle, a sphere. Oh, Kaylee has a question. So O2 is a molecule and a compound. Would NaCl would wait? No. So O2 is a molecule and a just a molecule. Sorry. Yes. NaCl is both. So NaCl, it is confusing. I just got confused. But NaCl has two different atoms bound together chemically, making it a molecule. And those different atoms happen to be different elements as well. It's just one atom of sodium, one atom of chlorine, making it a compound as well. So NaCl is both molecule and a compound, while O2 and everything else, let's say N2 is another one, those are just molecules because they don't have different elements. They just have one element with multiple atoms of that one element. So those are just molecules. Okay, great. All right, so we have models, whatever. So limitations, science has limitations. Basically, different variables we can't control, and measurement. Really, the biggest thing in science now is just how good can we get our technology to measure these things? Because we know a lot more that we just can't measure, like especially in physics and even in my field. So my field is cancer biology, and there are some things we want to measure behavior of different potential cancer drugs, and some of them we make are so strong that we can't accurately measure the affinity or the potency of that drug because our instruments just aren't that precise to go that far. So until they make better instruments, we're kind of limited by the technology available, but our science and understanding of the molecules, the atoms, and the biological systems has kind of surpassed our technology. So we need to, it's a balance between what we know and what we have the tools to learn about more. So what we know is a bit, in cancer at least, is more than the tools can do for us. So we're waiting for better tools. So that's interesting. And then there's things that can't be controlled that are external confounding variables. Now, I think the toughest field and the field to take and the data to take with the lightest grain of sand, what is it? Take it with a grain of salt, grain of sand. Yeah, whatever. I don't know. Is psychology. So many of you maybe you've taken psychology in high school, and you hear these studies. Oh, there's a study that says this about schizophrenic people, that they should take this drug, and this many % of them react to it. I think psychology is a great field. It's the most difficult field, in my opinion, because the confounding variable, the variable that can't be controlled, and what it is studying is the human condition, which it's crazy. We are human beings, yet we know so little about how the brain works. We know so little about getting the existence of human beings down to a science, yet we're trying to do that and then prescribing drugs for it. So really the only conclusion that we know for sure about psychology is everybody's different. Wow. Ooh. And like it took us hundreds of years of understanding how the mind works to figure out that, all right, all humans are different. If this one schizophrenic person responds to lithium and it basically cures his schizophrenia, another one might not at all, or might only 10% make a difference, and it doesn't make biological sense, but it's the human condition. And we're starting to learn that we have, you've heard of the placebo effect. We have we have a mind over matter kind of intangible effect on our own body. And everyone experiences that every day, where you have a crappy day, you feel crappy, you're in a bad mood, things start to ache, things start to hurt, you feel like your heart's racing, or you feel just like uneasy, maybe you can't think straight. It affects everything. You're like, your stomach hurts or whatever. But if you feel just good, something good happened, all that goes away. There's nothing wrong with you. It's just your mind over matter. Your mood and how you feel and how healthy you are can like change the way you think, and vice versa. So that's psychology, and we're learning more about that. And there's so many variables that we observe, and there's so many different ways of confounding those variables to controlling them. It's crazy to me. That's why I stick with chemistry. And in biology especially, the cells and the proteins, they don't have an opinion. They don't know what's happening to them. So I could deal with that science a bit easier. But yeah, kudos to psychologists and psychiatrists who do research on it. That's crazy to me. Okay, so here's a comment. So was there a study in the 60s when a doctor used iDopa on different mental patients? I think so. I'm not sure. Honestly, I don't know every study, but yeah, I mean, there's so much variability that I don't know anything. Okay, let's continue. Sorry. So approximate, I like this. Approximate lifetime risks of death. All causes, lifetime risk, 1. Approximate lifetime odds, 1 in 1, we all die. That's nice. But yeah, so death in the United States, there's different causes, of course, and cigarette smoking. Now, here's where this gets into. The cause of death is not cigarette smoking. No one dies from smoking a cigarette. People die from the diseases that cigarette smoking increases the likelihood of promoting, such as could be mostly lung thing, emphysema, lung cancer, throat cancer, things like that cause you to die. Smoking cigarettes doesn't cause you to die. It drastically increases the odds of you developing a certain disease. So yeah, this kind of, well, I mean, that's true for that and heart disease. Well, heart disease is the cause of death. Cigarettes are not the cause of death. Cancers are the cause of death. Motor vehicles and everything else would be kind of the peanut butter. Oh yeah, from allergy. People with peanut butter allergies. In that case, peanut butter doesn't cause you to die. The swelling of the allergy of the allergic response causes your airways to close off, and then you die that way. So it's not actually peanut butter; it's what it causes. Terrorist attacks, yeah, that's the terrorists cause that, not your body. Anyway, so that's kind of morbid, but this is a perfect segue to talk about COVID. Now, I could talk about COVID for a while, like biologically, but I don't want to go crazy on it. But the CDC just released a cool, not cool, but an interesting fact. So we all heard when COVID first started that, if you have an underlying condition, it drastically increases your odds of getting it and possibly dying from it. That's true. But we didn't know the extent of that because we didn't have enough data. Now we have enough data. So the CDC released yesterday or maybe 2 days ago, that 94% of the U.S. deaths of COVID-19 are people or patients that had very serious other illnesses, maybe emphysema or maybe lung cancer or heart disease, very serious illnesses that most of them were already in hospice care and end of life care already, or near it, or like retirement homes where they had all these diseases. And that's where 94% of the deaths were from not just underlying conditions like high blood pressure, serious underlying conditions. Now, this kind of throws off the stats a bit. Now, when you take that 94% into account and take the other 6%, which are healthy, basically healthy people, maybe a little bit older mostly, that got COVID and ended up passing away. That makes only 9,000 people. So still, that's a huge death toll, right? That's huge. We don't want to see anybody die. But 9,000 in comparison to the amount of people that got COVID, we're lucky it wasn't more. So we're lucky it's not higher. So that's actually good news that based on this statistic, COVID isn't as deadly to, let's say, normal, healthy people, and even people with kind of like maybe if you have like a little condition, like a heart murmur, or it could be high blood pressure, something that's not life-threatening. And even like diabetes is not life-threatening in most cases. Things like that. Your risk of dying from COVID is not as high as we thought it was, which is actually great news. It's a win for us to understand this finally. So that's good, but still wear your masks, obviously. But and it's terrible to get. So one of my friends got COVID, and he's like super in shape, works out all the time. He's my age, 25, and he got COVID. He's in the hospital for a week, and like he was hard to breathe, and like he had to be on a respirator. Like it can happen to anybody, but just from the statistical point of view, the causes of death are not as high as we thought they were, or not as COVID related as we thought they were for people that did die. So that's a good news in terms of the threat of the disease being less than we thought it was, but it's still not good because it's a terrible disease.
Is he okay?
Oh yeah, he's good. He's good.
Yeah.
This was like 3 months ago. Thanks for asking. And the reason why, and also one more thing. Here's why these stats are a little bit weird, and we didn't know this until now. The hospitals report more COVID deaths than they should. And the reason why is they want to get more funding. So that's big business for you. That sucks. But that's what they do, actually. And they've been doing that this whole time. And they just say, oh, someone else had COVID, but this guy, he died of heart disease or just old age and something happened and organ failure or whatever. Let's just say he died of COVID, just so we can increase the stats of COVID so we get more government funding for our hospital. That's not ethical at all, but that's what happens. Okay, let's switch gears and continue with the lecture instead of doing asides. Chemistry is important. We get it. All right. Hey, it is me. So research, there's different types of research, and I'll go through this kind of quickly. So there's applied research. So applied research is what I do, is we basically use all of our basic research and all of our things that have been established in the field to solve certain environmental or industrial problems, such as, for me, it's cancer. And for other people, for people that do green chemistry, it's cleaning up the environment. So using what we already have to solve newer and applying them to newer problems, hence applied research. The slide originally was this guy, George Washington Carver, did peanuts or something. I don't know, whatever, boring. Then we have basic research. So basic research is for the sake of knowledge, which is very important, which is the foundation of applied research. So Gertrude Elion, she worked with purines and found out their role in the cell with amino acids, not amino acids, with DNA. So that's very important. She was one of the pioneers in developing our theories and what we know about DNA and its role in the cell. And that led to my research eventually, right? That branched off into that knowledge is important for everything. And here's a funny GIF, because it was an old lady. That's not a good GIF. I don't know. I made these years ago, but you get a All right. Continue. So chemistry is the study of matter. We know that matter is everything that has mass and a volume. Great. Now let's get into details of units. So mass and weight are different things. Weird. But the mass is the amount of matter in an object. So I could ask a question that if I go from here to the moon, does the amount of me change? And the answer is no, because I'm still the same amount of atoms and the same amount of particles in my body, regardless of where I go. But my weight would change. So mass is definitive is specific to the object. The weight is the measure of the gravitational force on that mass. The weight is dependent on where you are, whereas the mass is not. So, for example, if I went to the moon like this picture, my mass would stay the same and my weight would decrease because the moon is less massive than the Earth. Hence, it has a lower gravitational force, meaning I would be lighter. So if I went on a scale on the moon, I would be lighter. So something that irks me is how you see this very common conversion of kilograms to pounds. That conversion is only true on Earth. So it's not a universal conversion because pounds is a unit of force actually, and kilograms is a unit of mass. Okay, next thing, physical properties. So we're going to be learning about physical and chemical properties now. So a physical property is very simple. You knew this before, is a property that a substance can have while being observed. So color, its mass, its weight, its length, stuff like that. Stuff that you can directly, in the macro environment, in the tangible environment, you can observe it, and it has these certain properties. So here are some examples. Your temperature, you can take the temperature of it, its mass, color, you can taste it. Not recommended for the lab, but I don't need to worry about that. It's online. Its odor, its boiling point, its hardness, its density. Things that are measurable from a physical point of view are the using our senses, our physical properties. Then you have chemical properties. So chemical properties are those that can only be studied while it forms a new substance. So chemical properties could be its reactivity, its charge, and things like that can only be observed by their reaction with other particles. And here's some examples of some properties. So you have rust, its ability to rust, its ability to burn, its ability to tarnish, its explosiveness, its toxicity, and its inertness. So we'll go over those. So rusting, we all kind of understand. It's really we'll learn about that more when we talk about oxidation reduction. But rusting is a chemical property that is involved with oxidation of iron. So, or oxidation of a metal is rusting. And usually we talk about iron. So we make the iron on the surface reacts with elements and reacts with the environment. And the oxygen from the environment creates these iron oxides, which gives it a rusting color. So that is a chemical process. Burning, same thing. You're combining oxygen with heat where it actually expels heat. You're combining oxygen with carbon-based material to form water and carbon dioxide and heat. Tarnishing, very similar to rusting, but with silver and sulfur. Explosiveness, so if you have nitroglycerin or TNT, things like that, those are compounds that that react together and explode. So carbon monoxide, toxicity, right? So toxicity is another chemical property. So you can only observe it by making it react with something, or unfortunately testing it on rats. So if you put carbon monoxide with the rat would die. And that's how we know it's toxic, by its chemical effects on the rat. Then you have inertness, which is kind of the opposite of toxicity because it doesn't react with anything. So argon, like I mentioned before, is one of those inert noble gases. So is helium, so is neon, obviously, and then you have other ones as well. Okay, so next. Now, physical changes. So we know what physical properties are. They're things that we can observe. Physical changes are things that change only the observations, but the chemical structure of whatever we're observing is still the same. For examples, melting, freezing, boiling, stuff like that. If you melt melt ice, it's still H2O. If you boil that water, it's still H2O. If you freeze the water again, it's still H2O. but the shape of it has changed. The freeness or the degrees of freedom of the particles have changed, but those particles are still H2O. So that's what we mean by physical change. And also another physical change would be the shape or state. So by state, we mean it's solid, liquid, or a gas. By the shape, we mean you cut a log in half. It's still a log. That's a physical change. So, okay. Classification of matter, you have the three main ones. You have solid, you have liquid, you have gas. So a solid has a definite shape and volume, and which you know that. And really, here's the thing. In every form of matter that we know, the molecules are moving. Even in a solid is moving. The molecules are tightly packed together in comparison to liquid or gas, and they are vibrating. And some of them are even moving a little bit more freely, but they are bound together so tightly that they have not much motion, and they're just kind of like a tight, like a cereal bowl where you fill it with cereal all the way. You can't really, and they're all kind of like interlocked. You can't really move it too much, but they do. Once the waves of the milk go by, they move a little bit. So that's kind of like a solid. Then you have a liquid, which has a definite volume but does not have a definite shape. So that increases the movement of the particles because you can flow liquid, right? So if you can pour out liquid, so the particles move together, but their intermolecular forces, the things that are holding the molecules together, are still strong enough to where water molecules don't separate from each other and just go wherever. If you pour water, it pours in a stream. In most liquids, you pour them, they pour in a stream. So they still have a lot of forces together, but they have more freedom and they do flow. And then you have a gas, which breaks all the rules, has neither a definite volume or a definite shape. This is because gases don't react with each other. And they don't, and they're very high energy. So compared to a liquid and a solid, and they have a large degree of freedom. So whatever gas you're talking about, if you take a breath, that CO2 will dissipate equally throughout the room. It will take time because there are other competing molecules, but it will dissipate throughout the room. So, and the gas will take the definite volume of the entire room and shape of it. So gas has really no boundaries. All right, so they are solid, liquid, gas. And then we have chemical change. So we have physical change, which is the changing of the shape or the state, the physical shape or state. What did I just do? Like melting, freezing, or cutting it in half. Then you have chemical changes, which are changing the chemical composition of compounds. So here's an example with the log. You cut the log in half, it's a physical change. If you burn the log, it is now a chemical change. So I'm going to cut to the chase. On homeworks and on tests, you might see questions. Which of the following is a physical change? Which of the following is a chemical change? For you, I would say for chemical changing, think of two things. Think of two concepts. One, can you undo the process? If the answer is no, it's probably chemical. Can you unburn a log? No. You can't get the CO2 and the H2O and the ashes and create a log again. So it's a chemical process. It permanently chemically changed the outcome, the original, so not the outcome, the starting material. Baking a cake on the left-hand side. Can you unbake a cake? No. You can eat a cake and transform it. That's another chemical change. But you can't unbake it because the molecules are already broken. The bonds have been broken and new bonds have been formed to expand the cake batter. So that is a chemical change. Other key terms are rusting, burning, caramelizing, I guess just for sugar, and then tarnishing. So rusting, burnishing. I like that word. Rusting, burning, and tarnishing are the three key things in chemical change. The three key changes involved in when we're talking about chemical changes. Those three. Okay. All right. Next, matter. So I want to say something cool. Before we go into matter, so I mentioned the example before where when you breathe, the air comes out, the gas molecules come out of your mouth, and then they dissipate throughout the room. I want to give you some perspective on that, because it's actually a really interesting process to understand. So when you breathe, let's take a trip through the air molecules. So an average gas particle in space, the air, every gas, there are millions and billions of gas particles. So I'm going to ask a question at the end, or in the middle. So listen. So there's millions of gas particles, and they're all around, right? We can see through them, but they're all around. When you breathe out, there are more, and those molecules are in competition with the other ones for movement. They're all moving. Everything's all moving really quickly. The speed at which the average gas molecule moves is 0.5 kilometers per second. So half a kilometer per second. So you guys are all assuming in New York City, I'm in Jersey City, New Jersey. That means if I breathe in towards the river, it would get to you in like 4 seconds, 4 or 5 seconds. Why doesn't it? So how come when I breathe, it doesn't get to the other side of the room immediately in that time, in the speed at which it goes at? So that's the question. Anybody have an idea? And then give a funny example, like why if someone farts that's like a kilometer away or on the other side of the room, right? Like 30 feet away, if somebody farts, you don't smell it. Why is that? Those are gas molecules. They should reach you 0.5 kilometers per second, right? Why don't they?
There's
Anybody?
Because there's other things that are around that are absorbing gases or changing it before it gets to you.
Close. So one of you guys said airflow. All right, that's getting in the right direction. But I think Evan nailed it, where other molecules block it.
Yeah.
So yes, good job, Evan, and good job everybody else. Those are good thoughts. So like I prefaced it with, there are millions and billions of air molecules, or not air, of nitrogen, oxygen, and gases that are in the way. And they're all moving at this speed. So that means there's a lot of competition. There is banging and clashing all over the place of different gases. So for the time it takes a fart, let's say, right, use an elementary example, an elementary school example, to reach the other side of the room may take a couple minutes or an hour or 10 minutes, but you won't smell it by that time. Why? Because the gases diffuse through space. So the same reason why when you shine a flashlight, it's kind of like a cone, and after 100 or 200 feet, you really can't see the light at all. You can't see 200 feet away because the photons dissipate in kind of the same manner as the gas molecules do. But the gas molecules have hundreds and millions of other gas molecules bouncing against them, blocking their movement. Just like Evan said, they're blocking the movement, and they're bouncing them in different directions, and it's just all chaos until they can diffuse throughout the environment equally or evenly disperse. And eventually they do take up the volume and the shape of the room or the container that they're in. So that's pretty cool to think about, how the air is just this bouncing around of molecules. And everything's kind of almost stationary, but it does move slowly. Now, this 0.5 kilometers per second does become significant. And you could think, all right, if any gas molecule is moving 0.5 kilometers per second, can't that hurt us? That's moving really fast, but we don't really feel it at all. So that's also the answer to this question of why can't we feel it, is because there's so many opposing forces and opposing molecules moving against it and bouncing off, that the 0.5 kilometers per second per molecule happens over the distance of maybe a couple of millimeters, even smaller than that, even micrometers. before they hit another molecule and bounce off. So the net motion is basically zero, or not much, unless you give something else a force. Now, here's another question. When can the speed of the gas molecules hurt us and hurt things? There's a couple of cases, but any ideas? Like the 0.5 kilometers per second, I mean, we should be able to feel that at some point, right? So can anyone think of an example of how that could hurt us? Think about the environment. Sun rays, not really, but you're on the right track thinking of the environment. So it has something to do with the environment. So what about, so the thing about air, what happens to air? Like just things that can happen to air. Not pollution, yes, that could definitely happen to air. But things that can hurt you, like physically hurt you, not like hurt your food sources, like physically hurt you. Not carbon. I'll give it a couple more tries. Any ideas? It's very simple. You're going to be like, oh, damn it, how didn't I get that? All right. 3, 2, 1. All right. The answer is wind.
Wind.
Yeah, duh, right? No, but wind, what wind is so when there's no wind, those gas molecules are just bouncing off like they are in the room, and there's just equal and opposite forces all over the place. But wind is the coordination of all these gas molecules moving in the same direction at that speed. If they all move in one direction, there is no reason for them to be hitting anything else. And they actually move at 0.5 kilometers per second in some cases, depending on how strong the wind is. Then you have tornadoes, hurricanes, which can destroy everything and kill people. So that is how these gas molecules can actually hurt us, by using their speed caused by wind. Their coordinated speed. They're all coordinated in one direction by wind. And how is wind generated? By pressure gradients. So if you have a high to low concentration of air pressure, it kind of forces the air in one direction at really fast speeds. This is what creates wind. So that's kind of crazy. All right. So enough about wind. That's just a cool fun fact. Now we are going to talk about the classification of matter. And there is a crash cam video on this. So all matter is composed of two types of classifications. You have substances and you have mixtures. Some textbooks like to call it pure substances. And I like that better because it really describes that they are purely a certain thing. Mixtures are just mixtures of other things. Now this slide is the only one that really is very comprehensive. Now a substance, there is elements and there's compounds. So an element, we know, is just, it's on the periodic table and it's just a pure elemental form, right? So this gold coin, assuming 100% purity, is 100% gold atoms. So that's an element. Other examples would be aluminum foil, just carbon, I guess, a stick of carbon. Then you have compounds. Compounds we know, are more than one element bound together chemically. Water is a compound because it's a sea of water molecules. So we know what that is. Now, mixture. There are two types of mixtures. There are homogeneous or homogeneous mixtures and heterogeneous. Or some people say it heterogeneous. I'm like, that's not how it's pronounced at all, but heterogeneous. Now, these classifications. So homogeneous means the same throughout. So geneous means throughout the material. Or means throughout, I think. I don't know. But homo means the same. So homogeneous, same throughout, same material. So this means that it is a mixture that is completely, well, equal. I mean, no matter what sample you take of it. So a good example that we can study every day is salt or sugar water. When you put salt into water, it dissolves. If you take 1/2 of the cup, there will be the same amount of atoms of sugar, or the same amount of molecules of sugar or salt than there are of the other half. So regardless of what sample you take, there will be the same chemical composition. That is what a homogeneous mixture is. Looking on the other end of it, heterogeneous, where they have a different composition throughout. Hetero means different, so different composition throughout. Now, if looking at this sand example, sand is a great idea, a great example of a heterogeneous mixture, because you can pick a rock from it, you can pick a shell from it. There are different, no matter what, or depending on what sample you take, there is a different result of different composition. So that's heterogeneous. Another example, a chicken salad. You have your salad, you have your lettuce, you have your dressing, you have your chicken, you have your croutons, you have chickpeas, I don't know, whatever else you want to put in the salad. But a tomato, maybe, I don't know. Now I'm hungry. But that's a heterogeneous mixture, because you could take either a tomato, or if you take another sample, it could be a piece of chicken. It's different throughout. We went over this already, atoms and elements. Now, the one thing we didn't see yet are the chemical symbols. In the upcoming weeks, we will become experts at the periodic table and the chemical symbols. But Cl is chlorine, H is hydrogen, and Mg is magnesium for now. I mean, that's what they are, but there's more, obviously more. There's 118 of them. Compounds, we know what they are. 2 or more elements. Molecules are 2 or more atoms. Mixtures, we just talked about this, how homogeneous are uniform in composition, where heterogeneous are not uniform in composition. Okay, so any questions on the, really this is the best slide summarizing all of it. Any questions on the classification of matter in this way? No? All right, cool. All right, next thing is units. So, in lab, we kind of talked about the units a little bit, but there are 7 base SI units. The SI units are similar to the metric system, but they're really the scientific international unit. That's what SI stands for. Scientific international base of units that we use in chemistry and in most sciences. So where is volume? What the hell? Volume should be on here. That's not a good chart at all. Volume's not on here. Volume is liter, but you can write that in. Volume liter. We're actually the SI unit for volume is meter cubed, but in chemistry and in really every other biological and really every life science, we use liter. So you get milliliter and stuff like that. But we have length is going to be meter, so M. Mass, the base unit is kilogram, not gram. Time is seconds. Temperature is Kelvin, which we'll talk about towards the end. Amount of substance, which we'll talk about in the next chapters, is the mole, M-O-L, or M-O-L-E is the name of it. See, look at the job I did on the abbreviation. So they took M-O-L-E, and then the symbol is M-O-L. Wow, it's so much easier. Then you have 2 that we're not going to cover in this course. Electrical current, which is the ampere. And then you have the luminosity, which is the candela. So named after the people that made them. And Kelvin is also that. There is no Mr. Second or Dr. Second or Mrs. Second that made the second. It's just kind of, I don't know who made it. I guess we just all agreed on it at one time. Okay. So these are the SI units. Now, here is where what you need to know comes into play. So here's what you need to know. The prefixes for the units, which some of them you may know already. Now, you don't need to know all of them. I would say the ones in pink or magenta and blue are the ones you need to be familiar with for this class. And I'll go over those. Now, going from the or we'll start from the middle. So you have the unit, which is, let's say, meter. We'll use meter as our base unit. So meter. A decameter is 10 meters. A decameter. A hectometer is 100 meters. You don't usually see those units, which is why I'm not going to make it required for the exam. Kilometer you see all the time. That's 1,000 meters. Mega, a megameter. That sounds funny. You don't really see that much, but you see mega of other things, such as a megabyte, right? So megabyte, megabit, things in computer world. You see that. Giga and tera, you also see in the computer world. So your phone or your laptop might have 500 gigabytes of a hard drive, whatever. Now SSDs are the new thing, but you have gigabyte, and then you have terabyte. So terabyte is also, you have hard drives in that size as well. And gigabyte, you also have memory and stuff like that. All right. So those are the higher units. So megabyte is 1,000,000 of the unit. So a megaliter would be 1,000,000 liters. A gigaliter is 1,000,000,000 of that group, of that unit. So a gigaliter is a 1,000,000,000 liters. And then you have tera, which is 1,000,000,000,000. And that's kind of easy to remember because they both start with T. So tera, trillion. So that's important. But to go the negative or the small scale, the decimal scale, is what we're going to focus on in the lab and with calculations in this class. Because most of the volumes and things that we're going to be measuring are in milliliters, milliliters, deciliters, things like that. So the deciliter or decimeter is 1/10 of the unit. So 1/10 of a meter is a decimeter. Then centimeter, which you should all be kind of familiar with, is 100th of the meter. So centi means 100, just like you have 100 cents in a dollar. The centimeter is 100th of the unit. So 100 centimeters equal 1 meter. Then you have milli. So milli doesn't mean million. Milli means 1,000th of. So you have 1,000 milliliters in a liter, for example. Then micro. Micro is 1,000,000th. So this is where that's 1,000,000. So a million microliters equals 1 liter. Then you have nano, which is the smallest that we need to know. And pico and femto, that's too small. Nano is 1,000,000,000th. So 1,000,000,000 nanometers equals 1 meter. So that's very, very, very small. So when we talk about nanometers, we talk about the radius or the size of atoms. That is how small atoms are. They're 1,000,000,000th of a meter stick. That's crazy. And we talk about the different, and even in that case, it's a couple of hundred of nanometers. Or sorry. 1/10 of a nanometer is like talking about lengths of atoms. Maybe so 1/10 or 100th of a nanometer. There's actually another unit for lengths of atoms. It's called the angstrom, and the angstrom is 1/10 of a nanometer. Or actually, no, wait, yeah, it's 1/10 of a nanometer. So that's crazy for how small it is. So cut to the chase, what you guys need to know and what you're going to do with these prefixes is you're going to have to do conversions with them. So pretty basic conversions, but hey, everything's not basic. This is the first time you're taking this class, but they could get harder is what I'm trying to say. Now, with these conversions, if I asked you how many centimeters are in 2 meters, you would be like, all right, well, there's 100 centimeters in 1 meter. Just multiply that by 2. All right, 200. And you'd be completely right. So we'll talk about more unit conversion later, and we'll build up on it. But this is just for the intro of what you expect for the homework and the worksheet to go over is this kind of unit conversion going from the different prefixes. So yeah, any questions on that? And the best way to learn is just from doing examples. Okay, so here's all the stuff. Oh, there's the cubic meter. There you are, the volume. But we're going to use liters most of the time. Everybody uses liters. I don't know why they even have cubic meters as the actual unit, but whatever. And then time is in seconds. So out of all 3 units of measurements, so you have the US standard, which is all messed up. You have pounds and feet and inches and all this crap, gallons. Then you have the metric system, which is very similar to the SI units. And then you have the SI units, The only unit that's the same for all three is time. So time is in seconds, minutes, and hours, and days for everybody on Earth. If it wasn't, that would cause a real problem with meetings. Oh, I thought we had class at I don't know, 50 microns or 50 hours or 50 hours, not hours. I don't know, stupid joke. But like if we had different units of measurement, it would be for time. It would in different countries. That'd be really bad for everybody. Okay, nanotechnology. That's good. There's not really much to talk about. But nanotechnology is just on the atomic scale, being able to manipulate matter. So nanotechnology kind of basically is biological sciences in essence, because we are manipulating and creating molecules to have a certain effect on the body. So any drug is an example of nanotechnology, because you take Advil, it kind of reduces your pain. How does it do that? It blocks your pain receptors. How do we do that? All right, let's make a molecule that binds to your pain receptors so that they can't do their job. There we go. So that's the idea of nanotechnology, manipulating matter at the atomic level to create an outcome. All right, so here's the first calculation thing you're going to have to do today. You kind of see the answer on the right side, but ignore the answer for now. I'm holding my hand up to block it, but you guys will see it anyway. This online learning stuff, it's got a learning curve. So density. So the density is defined as the amount of matter in an object in a given amount of space. So you have some objects are much more dense than others. So, and it's the equation for it is the mass divided by the volume. And usually this is expressed as grams per centimeter cubed. And something that's important is the centimeter cubed is equal to the milliliter, which is equal to the cc. So this is important maybe if you want to go into science and want to go into nursing or something, and you hear like, oh, nurse, give me cc's, give me 10 cc's of this, right? That means milliliters. So there's nothing weird about that. There's nothing super difficult about that. It just means milliliters, but cc is easier to say and it sounds cooler. So centimeter cubed is the same thing as a milliliter, same thing as a cc. Now, we use cc's and milliliters as the volume unit when we talk about density most of the time. But you could have density in any unit as long as it is mass divided by volume. You could have it in kilograms per liter. You could have it in megagrams per milliliter. It doesn't matter as long as it is the grams divided or the mass divided by the volume. And the density of copper is 8.94 grams per centimeter cubed. Oh no. So here. No. Can I oh no, I messed up. Okay, we're doing this one together, I guess. So if I were to give you the question, calculate the density of a metal sample with a mass of 18.96 and a volume of 4.31. You take the equation for density, mass divided by volume, you divide the two, and you get 4.4 grams per centimeter cubed, like that. Okay, so things like that would be a good example. Okay, so there hasn't really been too many calculations yet. In the worksheet, there will be a couple. So you'll work together on with your group on that. But this chapter, I've been kind of all over the place, but that's exactly what it is. It's kind of just giving you a sample of the different things that we're going to delve into going into the next chapters. And then we'll get more into detail about calculations, about exactly what every phenomenon is. The next thing we will learn about is energy. So energy is the ability to change matter physically or chemically. That's really broad. But there's two types of energy, which are the important ones. You have potential energy and kinetic energy. Now, potential energy is stored energy that is not being currently used. So it has a potential to become kinetic energy. And we can give you some examples on, I can give you examples on this. So if you take an object and you lift it in the air and just hold it in the air, it has potential energy. If you increase the height at which it's at and lift it up higher, it increases the potential energy. Because once you release your hand and it falls to the ground, the higher you have it initially, the kinetic energy, once you release it, it will go faster. If you release it from an inch above the ground, the potential energy it has is not very much. It just hits the ground, and that energy that was put on the ground from it hitting the ground is not going to be that much. So that's one that's one example of potential energy, is just dropping something, and before you drop it, it has potential energy. When you drop it, the potential energy gets converted into kinetic energy, which is the energy of motion. Now, there are other examples of potential energy. Those include food. So food is potential energy, because when we eat the food, what happens is our body metabolizes the molecules and uses the energy from the food, the potential energy stored in the bonds of the food, to move our muscles, to move our nerves or synapses, and to create metabolic processes. So that's potential energy in the form of chemical energy. And then you have kinetic energy, which is the other form of energy, which is the energy in motion. So by motion, I mean moving. So if you see a car moving or you're walking, that is kinetic energy. And that's a pretty simple one to understand. And a joke I make every year is you all have the potential energy to get an A in this course in the lab. Now it's your job to turn that potential energy into kinetic energy to get that A in motion by doing your homework and your classwork. Yay, I'm corny. All right, so the last thing that we're going to touch on in this class is heat and temperature. So how many slides do we have left? Oh yeah, cool. All right, so heat and temperature. So I'll preface with this. Cold doesn't exist. So making something cold is not a real thing. All you're doing is removing the heat to something else that's more cold. That's what making something cold is. If you think about an ice cube. So an ice cube, you put it in the water. The ice cube is not making the water cold. The water is making the ice cube warm. Because the way heat travels, the heat gradients, it always goes from a high source of heat to a low source of heat. So if you put an ice cube in, ice cube is very cold, the water is lukewarm. The molecules from the water will collide at very high speeds with the ice. What that will do is it will excite the ice molecules and make them move faster, eventually turning them into water. And that process repeats and repeats and repeats until the entire ice cube has melted into water, because the energy, the heat energy, thermal energy of the water has actually warmed up the ice cube rather than the ice cube cooling the water. So that's an interesting thing you can go home with today, is that coldness doesn't exist. Coldness is just the absence of heat. And to make something cold, all you have to do is remove the heat. To make something warm, all you have to do is add heat from something else that's warmer. So hence, you basically heating up an ice cube, and you're removing the energy from the water and putting it into the ice cube, which cools it down, which warms it up, which removing the energy from the water makes the water cooler at the same time. So that's another mind-blown thing. So hopefully. Then you have temperature. So temperature is the average kinetic energy of the atoms that make up the object. So temperature is a measure of heat. So heat is just the energy that is being transferred from, let's say, the warm object to the cold object. But the temperature is the measurement of that energy. So I will just say that this is a very important point. I'll write it down. So a very important point that energy, what was I going to write? So heat, well, no. Heat increases with molecular speed. Oh, do you have a question?
No.
Oh, okay.
Sorry.
Okay. So heat increases with molecular speed. So what this means is the faster you have molecules, the hotter they are. So talk about an ice cube going into water. The ice cube molecules are not really moving at all. The water molecules are moving a lot. Once the water molecules start to hit the ice molecules, it will excite them. It will speed them up. And it will bombard them to give them motion. Once they have motion, that gives them more heat. And what is temperature? Temperature is the measurement of that motion, the measurement of the average kinetic energy of the atoms. So the faster they move, the hotter they are. So that's a good thing to know. Yeah. And also their state is dictated by the boiling point and the melting point. So you can have a really hot piece of iron, like a solid, and it won't be liquid or gas because it's really hot, but that's because it didn't reach its melting point. And the melting point for metals, for example, is in the thousands of degrees at some points. Okay, so does that make sense? Kind of. So heat gets transferred to colder objects, making them hotter. And then temperature is the measurement of the average kinetic energy of those molecules. Okay, cool. And this heat can be measured. So heat is measured in either calories or joules. So a calorie, just like not the same as a food calorie, actually, but we'll see that in the next slide, and you can kind of see that. But a normal calorie is the amount of heat required to change the temperature of 1 gram of water by 1 degree Celsius. So it's a very one-to-one, it's a standard that the temperature required to make 1 gram of water, the energy required to make 1 gram of water change by 1 degree. Then you have a conversion from calories to joules. 1 calorie is 4.184 joules. So that's another important one. But I'll give you everything you need if you need to use that anywhere. Okay. So what's different about this versus the food calorie? So the food calorie always has a capital C. If you look at any nutrition facts label, you'll see that calorie is always capitalized. Mm-hmm. And what the calorie means in the food is actually a kilocalorie. So kilo, based on the prefixes that we just learned, means 1,000 of the unit. So 1,000 calories is actually 1,000 like lowercase calories is actually 1 food calorie. So the next time, let's say you have a friend or whatever, you're trying to like eat healthier and like have less calories, you say, oh, this drink has 100 calories. And she's like, oh, it's 100 calories, not too bad. He or she, whatever, 100 calories. You could say, whoa, it has 100,000 calories. You're going to really drink that. You're going to really have that drink. It's too much. That's 100,000 calories. And then he or she will freak out. Like, oh my God, what's 100,000 calories? Oh, like, where'd you get that from? It's like, well, because the capital calories actually means 1,000 little calories. So good question for you to think of is why the hell do they do that? And the answer is, I don't know. The only thing I can think of is they make the numbers smaller, right? But then if that's the case, you don't want to write 230,000 on this nutrition label where it says 230, but just say kilocalories then. Just make the unit kilo, just put like KC, kilocalories instead. So, but I don't know why they do that. It's a good thing to know. Okay, so the last thing we're going to look at is the temperature scale. So here are the 3 main temperature units that we are familiar with and we are most familiar with Fahrenheit probably. And the average body temperature in Fahrenheit, whatever, 98.6 is what you all hear. It's actually lower than that. It's like 98.2 according to this, but I think it's actually lower than that. My normal temperature is in like the 97s, like low 97s. I'm not dead. I think I'm not dead, so that's good. But regardless, we have Fahrenheit, and Fahrenheit goes from, and we'll talk about this in a second. It goes from the lowest possible temperature in Fahrenheit is negative 460, and the highest is really infinite. Now, you see this on the bottom. I guess we could talk about this first. Is absolute zero, right? So absolute zero refers to the lowest possible temperature, or the coldest that an object can get. And you can think, whoa, how is there a limit to coldness? All right. Well, think about what heat is, what we just learned. So heat is the average kinetic energy, thermal energy. It has a relation to heat being removed. So temperature has a relation to heat being added or removed. Shouldn't you think maybe there's a point where all the energy and all the heat is removed? That seems possible, right? You can't remove more than what's there. So there's got to be a 0 point. There's got to be a point where once you remove all the heat from an object, it's the coldest it can possibly be. And that is exactly what that is. So that's exactly what the lowest absolute zero is. It is the lowest point at which you remove all of the energy from an object. It will have that temperature of negative 460 Fahrenheit, negative 273 Celsius, and 0 Kelvin. So here is the reason why the SI unit for temperature is Kelvin, is because Dr. Kelvin came along and he was like, we know that there is a point where there's absolute zero, where you take away all the energy and there is no more energy to take out, and all the atoms have stopped moving. What is that point? So he did calculations, he did experiments, and he figured out that it was negative 273 Celsius. So this guy was like, you know what? I'm a scientist. I'm a cool scientist. I'm going to make my own unit based on Celsius. I'm going to be like, this is my unit called Kelvin, and it is the absolute scale for temperature. And it starts at 0. It has no negative numbers. It starts at 0, and it goes all the way up to infinity. So you can't have any negatives, which is a good tool. And he figured out that, all right, the easy way to do that is to basically just scale up the Celsius by 273. So the conversion, actually, I'll write this down, use my pen thing. So the conversion is Celsius plus 273, it's actually 0.15, equals the Kelvin temperature. So that is the conversion that Dr. Kelvin made based on his observations of the lowest possible temperature. And then you can see other things involved here, and we're only going to use Kelvin we will use Celsius actually in some calculations, but you'll know. So here's another question. A good question. If that's absolute zero, how cold something can possibly get? There's actually two questions. How hot can something get? And the answer is infinity, because there is no limit. Because we don't know the expansiveness of the universe, it could be infinite. If it's infinite, then the answer for how much heat you can put into something is infinite, because you could just take all the heat there is and it's endless. But if there is a limit, if there is a finite amount of universe, then there is a limit to what the maximum temperature is, but it's unknown yet. So that's pretty cool. That's question number one. Question number two is, how cold did we ever get it to? Or how cold has it ever been? Like, what's the closest to absolute zero that's ever been measured? So I'll give you some comparisons. Now, freezing point of water, 32 Fahrenheit, 0 Celsius, and 273 Kelvin. Let's use the Kelvin scale. So 273 Kelvin, right? And So we know we're very familiar with the differences in Fahrenheit temperatures, right? 32 is freezing. If you double that, it's 64. It's really comfortable. So the difference between freezing and comfortable is like 32 degrees. Now, the Celsius scale is a little bit more, is shorter, meaning each unit of Celsius corresponds to 1.8 units of Fahrenheit. So what that meaning the difference between, so we could say the difference between freezing point of water and the average room temperature, right? So a freezing point of water of Fahrenheit, you double it approximately, and it's the average room temperature. Or you add 30, you add 30, 38, 36. For Celsius, you only add 20, meaning the difference in each of the individual Celsius units is less. Or sorry, the difference in heat is actually more. So 1 unit of Celsius corresponds to 1.8 units of Fahrenheit. So that being said, basically each unit of Celsius accounts for more heat than Fahrenheit does. All right. So let's use that knowledge. Sorry if that was a really bad explanation, but whatever. Let's go down in scale. So for Kelvin, the units are the same numbers, just scaled up. 273 Kelvin is freezing of water. So that's already freezing cold. 233 Kelvin is negative 40 Fahrenheit. Negative 40 Fahrenheit is like Russian tundra cold. Like you need, if you don't have like a full, like if you're not wearing an elk, you're going to be freezing to death. So that's extreme cold for human beings. The coldest temperature ever recorded on Earth naturally has been 120 or negative 120 degrees Fahrenheit. And that was, I think, in the up in the Russian tundra somewhere. And so negative 120 Fahrenheit is around like 200, or like 190 something, 180 something in Kelvin. So 180, think about it, 180 is the coldest temperature on Earth, 180 Kelvin. And that is like, you'll die. You can't breathe that air. You'd freeze your lungs. Like you're dead. So that's like super dangerously cold. And like, meanwhile up here, there's like city shutdowns when it's like 10 below, like 5 below. We like freak out and like nobody goes outside. But this is extreme cold. All right, so now let's go outer space. Since we know the coldest temperature on Earth is negative 180, and we would die. Or sorry, positive 180 Kelvin. Going outer space, it gets colder as you go further away from the sun. But let's just say the average temperature of space around Earth is around maybe 5 to 10 degrees Kelvin. Think about how cold that is. The people who go into space, they don't wear suits to prevent radiation. They wear suits to prevent the cold from killing them. They have super insulated suits made of like space material that can block that cold. So that's crazy. That's like 10 degrees Kelvin. That's insane. We can't even fathom that amount of coldness. Then you go into deep space, like Pluto, right? Pluto, very far away from the sun. The temperature on the planet Pluto is around 2 to 3 degrees Kelvin. So we're approaching that 0 point. So now, a good question is, all right, what's the coldest? Like, professor, what are you getting at? It's 10 o'clock. Like, get to the point already. So the coldest temperature ever observed was actually in a laboratory at MIT. So on Earth, they made this big contraption that sucked out energy from protons, not even an object. They didn't put a pen in there and suck energy out of it. It was proton or a neutron, something extremely small. They sucked all the energy out using different techniques to the point of where it got to. I will write this number down. 0, 0, 0, 0. Oh no, that's not a 0. 0, 0, 0. Wait. not the last 0. 4 Kelvin. They did that. They got 4 billionths, no, millionths of a Kelvin. That's the coldest temperature that has ever been observed by human beings in the universe. It was actually at our labs. So kudos to us for being really smart. But you know, and I know that the aliens are way ahead of us, if you believe in aliens or not. That they probably are like, oh, 0 Kelvin, no doubt. Like, that's no problem. Like, we do 0 Kelvin all day. But theoretically, you can't reach 0 Kelvin because at that point, that's the point at which no molecular motion exists. And that's a problem for physics. There's a lot of physical laws that breaks, that there's no motion, that breaks string theory and a lot of other things that I don't know about. But I know that it's not possible based on the laws that we know. I mean, if you were to break them like using alien levitation, whatever, then maybe the aliens know more than we do. But that's where we're at right now. So that is pretty cool, right? Now we're going to end with a practice problem, which the answer is right here. Yeah, right. Okay, whatever. I didn't. Why isn't the animations working? Anyway, I'll figure that out. So human body temperature 37 Celsius. Convert this to Kelvin. So what we're doing is Celsius to Kelvin is very easy. We're just adding 273.15, and we get around 310. If we use, that's not even, well, without the decimal point would be proper sig figs actually, but 310 if you add those numbers together. So that concludes this lecture. I'm going to end the video